This manuscript present Al2O3 and TiO2 flux enable activated tungsten inert gas welding of 304 stainless steel plates. The abstract of the current research work is the work aims to explore the influence of weld parameters on weld bed geometry that includes weld bed width, penetrations and angular distortions, and mechanical and metallurgical characteristics for 304 stainless steel welds. The oxide flux seems to narrow the arc and thereby the current density increases at the anode spot that results in high weld depth. Introduction of the work. The gas tungsten arc welding is most commonly used process for joining the stainless steel components. It is usually suitable for the thin sheet due to its applicability, flexibility, and better economy, and normally it is used for welding hard to weld metals like stainless steel, aluminum, magnesium, copper, and titanium. Hence, in current research works, 4 mm thick 304 stainless steel plates were welded by ATIG method without groove preparations in a single pass, wherein the activated flux are self-developed and mainly consist of oxides that includes TiO2 and Al2O3. The investigations aim to explore the ATIG welding of 304 stainless steel and to analyze the influence of oxide fluxes and weld factors on the weld bed geometry. Materials and experimental methods. Figure shows the schematic illustrations of mixing and coating of the flux for the TIG welding process. So to create the bed on plates weld, ATIG welding was performed on 30 stainless steel plates. A machine mounted torch was used with standard 2% thorium tungsten electrode of 3.2 mm diameter and high purity argon at the flow rate of 15 liters per minute were fixed in all welds. The tip configurations of the electrode was blunt point with 45-degree include angle. The table lists the weld process factor which has been used in the current research work. Result and discussions. The TIG weld cross sections with and without oxide fluxes for 4 mm thick stainless steel 304 plates are shown in figure. It has been observed that in a ATIG weld morphology, there is a major variation in the weld depth and bed width. With the use of TiO2 oxides, the weld depth increases and the bed width decreases and have peanut shell type shape. With respect to conventional TIG welding, there is a higher improvements in the penetration capability function with the use of TiO2 that is up to 115%. Figure illustrates the central part of the welding arc clearly in glowing zone that occupy almost the entire length of the welding arc without flux and with TiO2 composition. This zone is commonly considered the plasma column which forms when the shielding gas is heated to ionize electrons and positively charged ions. Figure 4 shows the effect of Al2O3 flux on welding arc and fluid flow. So here the TIG welding process with active flux which contains the Al2O3 powder that seems unable to reduce the anode spot and constrict the plasma column, leading to the relatively wide and shallow morphology of the weld in comparison to the conventional TIG welding. This result can be attributed to the alumina oxide particles in the weld pool during the TIG welding with Al2O3 powder that has been represented inside this figure. This figure illustrates the influence of weld depth to plate thickness ratio and angular distortion on angular distortions in the stainless steel plate of 304 with and without flux. It is clearly observed that The activated TIG welding results in reduction in angular distortions of the weldment. It is observed that the weldment produced by TIG welding with TiO2 and Al2O3 has better mechanical properties such as ultimate tensile strength than the TIG weldment produced without activating flux. At all arc voltages, raising the welding current from 180 to 220 ampere will affect and enhance the tensile strength of the materials. The experimental results for the hardness of the TIG welds with and without flux are shown in the given figure. Here the findings reveal that the oxide flux had no discriminable effect on the hardness of the stainless steel weld. In both oxides and Al2O3, TiO2, the radiography investigations reveal the lack of penetrations and insufficient fusion in TIG weld joints that has been illustrated in the given figure. This figure represents the microstructures of 304 stainless steel weld metals generated with and without flux, as well as the observed delta ferrite content. In all the cases, the austenite matrix microstructures and Vernacular delta ferrite morphology typical of this material class were found. However, there was no significant difference in the microstructure between the conventional TIG weld metal and the activated TIG weld metal. The figure 11 represents the ACM images of the fracture surface. Conclusion of the current work. The experimental results and conclusions are summarized as below. The use of TiO2 resulted in significant increases in the weld depth and decreases in the bed width, as well as the greatest improvement function in penetration, whereas with the use of Al2O3 resulted in deteriorations in penetrations and excessive slack when compared to the conventional TIG welding for 304 stainless steel material. When using ATIG welding, the physically constricting plasma columns and reducing the anode spot tends to increase the energy density of the heat source and the electromagnetic force of the weld pool that results in relatively narrow and deep weld morphology compared with the conventional TIG welding. The activated TIG weld can increase the joint penetrations and the ratio of weld depth to width, decreasing the angular distortions of the weld metal significantly. Better mechanical properties are retained by using ATIG weldments. The ATIG welding can increase the retained delta ferrite contents of stainless steel welds. The optimum set of parameters for oxide fluxes TiO2 and Al2O3 are at 180 ampere to 20 volts, 0.75 millimeter and 220 ampere 30 volt 0.75 mm respectively, giving the better weld characteristics.